Morning class, and welcome to this lesson on circular motion on a vertical plane. Today we will be able to set up free body diagrams for objects that move along a vertical circle for the four main points of the circle. So let's just clarify what a vertical circle is. Imagine for a moment that you have a cup of water or a bucket, okay, and you attach it to a string, and this bucket is full of water, and you are swinging it in a vertical circle that goes above your head and below, above and below. I know that the ground is right here, so just ignore that for now. So this is a vertical circle. It is a circle vertically aligned with how we stand up. So simple enough, right? Well, what we're going to do here is, because it's a vertical circle and not a horizontal circle, gravity is going to come into play here, because vertically, gravity always works in that y direction, right? The y direction, gravity is always pulling down. We have talked about this over and over again when discussing forces. So because this object is subject to gravity as well as centripetal force, so we have gravity and centripetal force here, we need to set things up a little bit differently. So what we're going to do is we're going to discuss the four main points, essentially the 6 o'clock, the 3 o'clock, the 12 o'clock, and the 9 o'clock position. The four main points around the circle. Okay? Four main points around the circle. So let's do that. So same scenario here. We have a bucket attached to a string, and this is going in a circle around like this. So let's call these points 1, 2, 3, 4. Okay? Points 1, 2, 3, and 4 as we go around. Well, point 1. Let's do this color-wise. Point 1. At point 1, right here, this object is going to have a force of tension pulling it in and gravity pulling it down. Okay? Tension pulling it in, gravity pulling it down. Now, if we're discussing centripetal force only, so remember, we're in the circular motion section. We are discussing centripetal force. So what is the centripetal force for point 1? Well, centripetal force is the tension, because centripetal force is pulling it towards the center. Centripetal force is pulling it towards the center, and the only force going towards the center or in the x direction at this point is tension. Gravity is going down. Gravity does not contribute to centripetal force at all. It's contributing as a force. It's there. But as far as we're concerned with centripetal force, tension is the only one. So if we had to calculate the tension at this point, tension and centripetal force, tension would equal mv squared over r. Done. Okay? So you can probably already tell that at point 3, we have the same exact thing. Centripetal force is equal to tension, and tension equals mv squared over 2. What's that about? Over r. So at this point right here, same thing. Tension is pulling it in. Gravity is pulling it down. Gravity does not contribute, does not play any sort of role in centripetal force, because it is in the y direction, tension is in the x direction. We know that we don't combine x and y vectors. We look at one or the other, and then we may combine them some other time, but in this case, tension is the only thing contributing to centripetal force. Okay? So I hope that's good. We got that out of the way. Well, now let's look at point 2. Point 2. At point 2, tension is pulling it down, and gravity is pulling it down. So these are both going in the same direction. So this is my free body diagram right here. Tension is going down, gravity is going down. It's accelerating. So T plus mg equals mv squared over r. T plus mg equals mv squared over r. So both of these are contributing to centripetal force. Now, the most likely question, the most likely question we're going to get is, what is tension? Well, based on that equation right there, tension equals mv squared over r minus mg. T equals mv squared over r minus mg. So we can tell from this right here that the tension is going to be less at point 2 than it is at point 1 or point 3. So the tension is going to be less than at point 1 or point 3. Okay? Tension is going to be less. Oh, I should clarify that a little bit more. Tension at point 2 is going to be less than point 1 or point 3, because at this point tension's pulling it down, but so is gravity. So it's like tension has a helper right here. Okay, so tension is, if we have the same speed, same radius, same speed, same radius, tension isn't the only force pulling it in. Gravity's helping it, so tension is going to play less of a force. Okay, so for example, let's say the tension at point 1 was just 10 newtons here, 10 newtons here. Well, if 10 newtons is required to make this go centripetally, well then, let's say gravity is 5 newtons. That means gravity is only going to be, that means tension is only going to be 5 newtons, okay? Because the centripetal force is going to be 10. So at point 2, there's going to be less tension because gravity is helping it. Gravity is helping it. I hope you can see the logic in that. So let's erase all this, and let's do our last one. Let's do blue. Point 4. Oh. Point 4. Tension is going to be pulling it up, and gravity is going to be pulling it down. So at point 4, we're going to have T minus mg. Why is it minus? Well, T is, we're going to call up positive, down negative. So T is positive, down is negative. So T minus mg equals mb squared over r, and T equals mb squared over r plus mg. mb squared over r plus mg. So you can see that point 4 and point 2 are the opposite. Point 4 and point 2 are the opposite because at the bottom of the circle, the tension is pulling it up, but it's fighting gravity. Gravity is kind of keep pulling it down. Tension has to keep pulling it up. So there's going to be more tension at the bottom of the circle than at the top of the circle. There's going to be more tension here than on the sides because the gravity is actually going against tension now. So whereas before it was helping it, relieving the tension, now it's going against it, and so it's adding on to it. So if you've ever swung anything with your arm back and forth, if you've ever taken your arm, draw your arm right here with your awesome hand right here, and you swung something, well, you're holding onto an object and you swung it back and forth, you might notice your arm feels the most stretched out. It feels the most force at the bottom of the swing. It feels the most force at the bottom of the swing because that's where gravity is going completely against tension. So these are our equations right here. We have point 1 and point 3. T equals mv squared over r, and then we have point 2. We subtract gravity because gravity is helping it out, and then at point 4 we add it because gravity is now going against the tension. So you might notice, I'm going to clear this. You might notice that on this circle, if we just focus on point 2 and point 4, if you remember our elevator problems. Person standing on a scale in an elevator. If the elevator is going up, if it's accelerating up, there's going to be more of a normal force. So there's more normal force. Okay? So this is just like at point 4. Okay? Just like at point 4. Because like at point 4, if we did our free body diagram, we would have normal force going up, gravity going down, And if we set this up, it's accelerating upward. So we're going to call up positive, down negative. So that means normal force minus mg equals ma. Not mv squared over r, because this is linear, not circular. And then so normal force is going to equal ma plus mg. So when it's accelerating upward, just like at point 4, the normal force would equal more. And if it was accelerating downward, same thing, normal force mg. Okay, normal force in mg, we're going to call mg positive and negative because it's accelerating downward. Mg minus n equals ma, so minus n equals ma minus mg, and then we can flip the signs here, n equals mg minus ma. You'll notice here that we are subtracting these two numbers. We will be subtracting these two, so it's going to be a smaller value. So this value x is going to be less than this value y over here, because here we add them together. So just like in an elevator, when you go down, you feel weightless for a moment because acceleration is going downward. You're relieving your weight. Same thing as point 2. Okay, same thing as point 2. Now there's only a couple other things I want to mention. Oh, by the way, there is this figure in the book. This is, I believe this is figure 5.21 in your book. So if you get confused, you can always reference this. This is exactly what we just covered. But I just want to cover one more thing. Sometimes we talk about cars being on a loop. Sometimes or a motorcycle goes on a loop. Okay, guy on a motorcycle. Okay, engine down here. Okay, instead of tension, well, what is it at each point? Well, instead of tension pulling it in, it's going to be normal force pushing it in. And we're going to have the exact same equations. Normal force equals mb squared over r. Normal force equals mb squared over r minus mg, right there. And at the bottom, normal force equals mb squared over r plus mg. Same exact thing, except now it's normal force instead of tension, because it's on the road is pushing it as opposed to a string pulling it. Okay. There's only one more thing I want to talk about. If we are putting this string, we'll go back to the string here, and some questions say, what is the minimum speed? What is the minimum speed, or I guess velocity minimum? What is the minimum speed to make the object go in the circle? And really what they're talking about is what is the minimum speed to get past this point? Because you could imagine if you were spinning like a bucket of water around, at this point, if it wasn't going fast enough, instead of spinning around, it would just come crashing down, right? Because gravity would take over. So it has to be going a certain speed to keep going. So whenever it talks about minimum speed, what we're really saying is the tension is going to be equal to 0. The tension is going to be equal to 0, because at this point right here, if it's the minimum possible speed, at that point, the only thing pulling it down is going to be gravity. And tension is going to, this is when the rope is going to go just a little bit slack. Just a little bit slack, and then it's going to have just enough speed to get to the top and then keep going back around. Okay? So with minimum speed is going to be tension equal to 0. Or if we were on a track, let's erase this piece right here. Let's erase this right here. If we were on a track, and what is the minimum speed to make the object go in the circle, or to make the cart, or the roller coaster go in a circle, at this point right here, this is when the cart would just come off the track. It would just make it to the top and then come around to the other side. So if it's just coming off the track, that means normal force is going to be equal to 0, or not. Normal force is equal to 0. So if you ever see these things in a problem, minimum speed, be careful with that, because what they're really trying to say is tension is equal to 0 or normal force is equal to 0 at this point right here. Okay? So that's just one of those things that they sneak in there, and it's easy to miss because you're so focused on the equations that you forget that, oh wait, minimum speed means it's just enough to get by, so that means tension is 0 or normal force is 0.